here we have two quantities. We have the instantaneous fractional yield.
Four.
And we have, which we defined as RR over RA, plus or minus, so as to make it positive. And we have the overall fractional yield, which is capital Phi R over A. And that we said is defined as, really we should define it if we have a non-constant density reactor as FR out minus FR in over plus or minus, again, so as to make it positive, depending on whether A is a product or reactant, of FA out minus FA in. Now, the reason why I don't write explicitly, the reason how we know that, well, clearly little phi only depends on kinetics because these are the rate functions. The reason that we know that capital Phi depends not only on the kinetics but also on the reactors, or the reactor parameters, is because it involves the F's. So the F's, I have to get the F's from the design equation. How do I get the F's? Where do I get FAR out and FA out? I get FR out and FA out from the design equation. And the design equation involves tau, which is CAV over F. And it involves the right side of the equation, which involves all the kinetic parameters. And this, they both come from the design equation. Gives me these functions. The design equation, that's if it's a single reactor. If it's a multiple reactors, it involves the design equation for all the reactors, as well as any piping. Design equations and piping. Separators, etc. Question?
When you look at this, for FA out minus FA in, it can be a reactant as well as a product.
Right. It depends on what's convenient. It's your choice. There isn't a right answer and a wrong answer. Often you have many choices. You just want something that's useful. Usually there's more than one thing that would be useful.
But if the selectivity, if two products go faster and faster as the concentration of A goes up, but one goes.
What do you mean goes faster?
Are produced faster. Let's say one has a rate of an order of 2 and the other an order of 2. Then the fraction is.
So you're talking about say A goes to B with K1 CA squared and C with K2 CA cubed.
And the fractional yield of B with respect to A and the fractional yield of B with respect to C will give us.
They're different expressions, but they won't give you different conclusions. As long as you ask a reasonable question. If you ask a question, for example, how big should the reactor be, or how big should the reactor be to get more B, a certain percentage of B relative to C or relative to A, you're going to get, if you phrase the question properly, you'll get the same answer.
I'll probably see that in the.
Yeah, and that's why there's homework. That's why we create homework. Other questions? Okay, so let's just look graphically. Now, of course, in constant density cases, then I could divide top and bottom by volumetric flow rate, and then I have concentrations. But in general, capital Phi should be that. Now, we looked at specific types of reactors where we calculated capital Phi. So we said for CSTR, we said that phi R over A is equal to what for CSTR? I'm sorry also. Oh.
for the CSTR is 1 over the big phi, talking about, right? Yeah.
Big fun.
1 over the concentration of A in, or this concentration of A out. The sum of
A single CSTR.
a single.
One CSTR.
Wow.
It's out, the concentration of the initial concentration of the product minus the initial concentration, the concentration of the.
Okay, time for a quiz. Take out this paper.
Yep.
You guys are responsible today. I'm really tired. I'm really tired of people not looking at their notes. Close book.